This morning I sat in my favorite coffee in the North German Lingen, read my physics book and burned my tongue on the much too hot coffee. Damn shit temperature. But what is temperature physically? Back home I printed out directly the Wikipedia article of the temperature. I quickly remembered that I was taught that temperature is the movement, oscillation and vibration of the molecules in my coffee. A little further back in the article I came across this formula. The reciprocal of the temperature is equal to the partial derivative of entropy by internal energy. Every day we read about the temperature in the newspaper. It's familiar to us. But when I tried to really understand temperature, I realized that its path leads deep into theoretical physics. In the formula we describe the temperature, or better the reciprocal of the temperature, by the entropy change due to the energy. But what is entropy? My professor said it was something like the disorder of the universe, but he also added that it doesn't really describe it very well. I would say that entropy would answer the question how much we know about the universe. What is the information content of the universe in bits and bytes? The formula, which is on Ludwig Boltzmann tombstone, is that the entropy S is equal to the sum of pi I times logarithm of pi I and then multiplied by k Boltzmann. Pi I are the probabilities for each microstate in which the coffee can be. Interestingly, the sum term is equal to natural logarithm of 2 times the information content H of the coffee. K Boltzmann is simply a constant by which this is multiplied. Entropy is a multiple of the information content H. The information content H of a message should now explain what the Boltzmann formula means. It was introduced by Shannon. I want to explain simply now this term that already appeared in the Boltzmann formula. My dad often gives me brain teasers which I have to solve, and when playing cards he gave me the following one. The game is called Ask Smart. You have a 7, a king, a queen and a 6. I shuffle the cards. Which card is on the top? I look at the top card and you have to find out which card is on the top with as few yes or no questions as possible. What is the smartest way to ask? While you are thinking about it, I will give you a second task. We play Ask Smart again. This time you have 4 jokers, 2 kings, a 3 and a 6. The colors don't matter. How can you ask now in the smartest way with only yes and no questions which card lies on the top? But first I look at it. In the evening, thanks to Shannon's help, I made a plan for Dad's task. I ask, is it ace or 7? 50-50, Dad says yes or no. He says yes, I ask, is it an ace? If he says yes, it's an ace. If he says no, it's a 7. If he answers no to the question, is it ace or 7? I ask, is it a king? If he says yes, I know the king is on the top of the cards. If he says no, the queen is on the top. With my strategy, I always need exactly 2 questions. If I would ask for each card separately, I would need 2.25 questions. The second problem is a bit more complicated. I ask first, is it joker, because then I'm at the one half of the cases already at the end if Dad says yes. If he says no, I ask, is it a king, because there are more kings on the remaining cards. If he says yes, I'm done and I know that the king is on the top. If he says no, I ask if a 6 is on the top. If he says yes, it is the 6. If he says no, it's the 3. By my strategy, I need with one half of the cases only 1 questions. In 1/4 of the cases, 2 questions, and in the other quarter of the cases, 3 questions. If we add this together, we get an average of only 1.75 questions. This means that one stack of cards has an information content of 1.75 bits and the other one of 2 bits. 1 bit is a 1 or 0, a yes or no question. Suppose the cards would now represent the microstates in my coffee. And the queen represents a molecule configuration in which it dances like a queen, and the ace represents one in which the molecules are vibrating. Then the 1 cards would have an entropy of 1.21 K Boltzmann, and the other cards would have an entropy of 1.38. Since the molecule configurations in my coffee cup are really complicated, I will explain the temperature on a classical pendulum. With this model, it's easier to imagine what temperature is. The inner energy U of the coffee is represented by the energy of the pendulum. The energy of the pendulum results from its potential and kinetic energy formulas. Here phi is the angle, L is the length of the pendulum, and m is its mass. G is the gravitational constant. The entropy S, which asked in the coffee in which quantum mechanical states the coffee molecules are, is replaced by the question in which green box the pendulum is. We now ask ourselves where the pendulum is if we know the energy. How many yes-no questions do we have to ask to find out which box it is in? We don't have to ask if the pendulum is at the top, since it can't be there. It doesn't have enough energy. At the bottom, the pendulum is faster and is therefore there less long. The probability that it is at the bottom is therefore lower. If I now reduce the size of the green boxes further and further, we get a resistance probability density of the pendulum. This can be seen above. The probability that the pendulum is at 1.9 radian is the highest because it stays there the longest. The probability that is at the top is 0 because it never stays there. We can then plug in this function into the differential entropy function and get an information content of 0.503. Nevertheless, with a small information content h, we can tell more exactly where the pendulum is. In the evening, I have calculated two pendulums with the most different energies, how often I must ask to know where the pendulum is if I know the energy. We see 4 pendulums with higher energies from the left to right. With small energies, I can tell exactly where the pendulum is. It's down. I don't need to ask many questions to find out where the pendulum is. If I increase the energy, I need to ask more questions. But if I increase the energy so much that it almost always stops at the top, I know more about the locations of the pendulum. It is most likely at the top. It is interesting that by increasing the energy, I know more about the system. If I increase the energy more and more, it is almost everywhere with the same probability, and I know the least about the location of the pendulum. We remember that 1 divided by natural logarithm of 2 k Boltzmann t is nothing else than the derivative of this graph. For the second pendulum, the derivative is plotted as a tangent, and it gives the temperature of 1.3 times 10 to the power of 24 Kelvin. Coming back to quantum mechanics, we need to understand what it means to make a measurement in physics. We take the well-known double-slit experiment, where the electron goes through one slit and the other slit at the same time. Measurement means to position a detector in such a way that it asks a yes or no questions. If we now have a triple slit, then the electron again goes the 3 possible ways at the same time. This time we can again position a detector to measure if it went through a slit or not, to ask a yes or no question. In the first experiment we need on average 1 question or measurement to find out which slit the electron went through. For the triple slit we need an average of 1.66 measurements. A coffee is, now just as the electron goes all possible ways at the same time, in all molecule configuration or quantum mechanical states at the same time. To find out which state it is in, we need measurements just like in the double-slit experiment. Entropy now tells us how many of these yes-no measurements we need to make. What is now temperature summarized? Who or what can I curse at my 2-hot coffee? Temperature answers the question how many times the number of measurements increase when we increase the energy to know in which state the coffee is.